One more time, good afternoon, dear colleagues. We start new session of our scientific seminar, and today we have talk from Anna Velichko. Please, Anna.
Yes, thank you. Thank you a lot that you're coming. I'm going to show you some results I got while I working with Narisa Dechia and Yves Leva, these two people, at the Geneva Observatory. My talk will consist of two parts. The first one is the observational side. I will make some review of the results we obtained from observations. And the second part is the ongoing project about constraining the observations with the use of hydrodynamical simulations. So in the Milky Way and nearby galaxies, we can constrain their properties via observations of individual stars. While in distant galaxies, it is impossible to obtain any information about individual stars. Instead, we can study their interstellar medium, or ISM. Yes. Because focus on alpha elements, with this slide, I want to explain you why alpha elements are very important in studying galaxies. Alpha elements and iron are produced via different channels with different time scales. As a result, the ratio alpha elements over iron changes with time, with galaxy evolution, and with metallicity, because metallicity is also increasing with time in galaxies. Alpha elements are mainly produced inside massive stars with short lifetimes, and they are mainly released into the ISM via core collapse supernova explosions. At the first phase, when only core collapse supernova contribute to the abundance of elements, we observe alpha elements overabundance, and alpha over iron ratio is constant and forms plateau. Then, after about 1 gigayear, when supernova 1A starts to explode, the abundance of alpha elements relative to iron gradually decreases. And the transition point between these two regimes is called the high alpha mean. And the important thing that the position of the high alpha mean is sensitive to the early star formation rate. If the star formation rate is high, then more metals have time to be formed during the first phase, which results in the high alpha me to be located at higher metallicity. And in turn, star formation rates are higher in the more massive galaxies. So we expect that in more massive galaxies, the high alpha me will be located at higher metallicities. And then this function goes to the low alpha plateau, but we will focus on the high alpha me. With this slide, I show behavior of alpha elements over iron in the Milky Way and in nearby galaxies. You can see that it's in previous slide, it's very simplified because, for example, at low metallicities, we observe quite a large spread in the Milky Way. And in dwarf galaxies, we can observe bumps in the low alpha plateau because of burst star formation. One of the ways to study distant galaxies is via damped Lyman alpha systems, or DLA. DLA consists of a galaxy and background quasar. The light from the quasar goes through the galaxy to the observer, and the ISM is imprinted in the quasar spectrum in form of absorption lines. as shown in the right figure. In case if column density of neutral hydrogen is higher than 2 times 10 to the 20 per centimeter squared, hydrogen is mainly in a neutral state, while other elements are also mainly in their dominant states, and other ionization states are negligible. So, so we don't have to take into account other ionization states when we calculate column densities of all the elements. DLAs also have other advantages. For example, absorption spectra provides very detailed gas chemical composition, and we can obtain, measure abundances of different elements even from very weak absorption lines. And there is no selection effect in terms of galaxy mass or brightness. With DLAs, we can detect both faint galaxies, which are low mass, and bright galaxies, which are high mass galaxies. In our study, we used column densities of a number of elements observed by Christina Konstantopoulou. In total, there is nothing here, but in total we have 140 quasar-DLA systems. The main problem in proper determining abundances in the ISM is the depletion by dust, because some fraction of each atom is withdrawn from the gas phase and is instead incorporated into dust grains. And we have to take this effect into account. Annalisa Dechia et al. Developed quite simple and effective method. They call it relative method, which allows to derive the total metallicity and strength of depletion in the ISM of DLAs from overall distribution of chemical elements depending on their refractory index. Refractory index means that the more refractory the element, the more it is incorporated into dust grains, and opposite for volatile elements. That's why we see this slope. So the blue line is linear fitting to this data, and we can see that elements have quite a large spread, mainly because of nucleosynthetic peculiarities of alpha elements and manganese. You can see that alpha elements, titanium, silicon, and sulfur, are systematically shifted upwards with respect to the blue line, to the best fitting line. So in this system, we observe alpha elements overabundant, while manganese is underabundant because it's normal for manganese. Manganese normally behaves opposite to alpha elements. We modified this method as shown in the right figure. Here we divide all the elements into 3 groups: alpha elements, iron group elements, and other elements. Despite some small differences in nucleosynthesis of alpha elements, we believe that their abundance pattern is quite uniform. So we think that the best way to obtain the strength of depletion or the slope only from fitting of alpha elements. Then to obtain the total metallicity, we shift this blue line to the value averaged over iron group elements as shown by the red line. And then to determine the total metallicity, we look for the intersection of this line, this 0 point. Yes, but for correct application of this method, it is highly important to have measurements of titanium, because this is the most depleted element, and at least one more alpha element to provide the large wide spacing along the x-axis for more reliable fitting. So from 140 systems, we selected 24 objects for which there are measurements of titanium and at least one other alpha element. And this system, this subsample we called as a golden sample, and we perform the main analysis for the golden sample. Sorry. We also need an information about masses of these galaxies. But the problem is we can't determine masses of the galaxies from absorption spectra. Instead, we have measurements of velocity width, or delta-V90, which are velocity intervals encompassing 90% of the integrated optical depth, as shown in the figure. Velocity width characterizes dispersion of dynamical velocities. So we can roughly use delta-V90 as a proxy of the galaxy mass. Then we divided our golden samples by delta-V90 into low and high delta-V90 subsamples with the cutting point at 100 km per second. From the relation of delta-V90 versus mass obtained by Arab-Salmani, we can conclude that delta-V90 equal to 100 km per second corresponds to stellar mass of a galaxy of 10 to the 9 solar masses. The main result we obtained 4 alpha elements, as shown in this figure. Yellow and blue points correspond to the high and low delta-V90 subsamples respectively. You can see that yellow points are tend to be systematically shifted with respect to blue points. Indeed, after fitting this data with these functions, as shown in the figure, we obtained the difference of 0.8 dex. So this is in agreement with our expectations because more massive galaxies show an alpha element E at higher metallicities than less massive galaxies. And this is the main result we obtained in our previous study. We also obtained one more interesting result for zinc over iron. From the literature, we knew that zinc tends to behave partially like alpha elements, but with smaller amplitude. This is exactly what you can see in this figure. Indeed, the yellow points are systematically shifted with respect the blue points, and the amplitude is smaller than for alpha elements. In this figure, I show manganese over iron. You can see that manganese is underabundant in all of these systems, and this is a bit contradictory to our expectations, because we expected that manganese should behave opposite to alpha elements. And from this figure, we know that in some systems, supernova 1A contributed to the abundance patterns. So we expected to see some hint on of decrease for manganese over increase for manganese over iron. But we see this increase so this figure is for the golden sample, and this figure is for all objects from all samples. And you can see that manganese over iron starts to increase at about metallicity minus 0.7. These results are published. You can find these papers using this QR code. And now I will show you some results we obtained in our ongoing project. The problem that it's difficult to measure luminosities, masses, and star formation rates of the DLA counterparts, because to measure these values, we need to obtain emission spectra, which is quite difficult to do. And it has been done for a few systems, which are the most massive and most bright and brightest systems. Instead, we can use hydrodynamical simulations to constrain the observed data. In our project, we use the GEAR hydrodynamical simulations developed by Ifriva and Pascal Yablonka. We selected from their samples 5 galaxies with different stellar masses to cover the wide mass range between masses equal to 6.1 and 10.8 solar masses in the log scale. We selected these galaxies at 6 redshifts between 4.12 and 0.33. I forgot to mention that the galaxies, the DLAs that we observed are at redshifts between 1.6 and 3.4. So this redshift selection is also to cover the range of our that spent our DLAs. In this figure, I show distribution of gas in these simulated galaxies at 2 end redshifts, at redshift 4.12 and 0.33. There are some kind of extreme cases. One is for the most massive galaxy H000, which has an elongated shape at redshift 4, because at that moment it consisted of 2 merging galaxies. But then these galaxies had been merged by redshift 4. And you can see that at redshift 0.33, this galaxy is within a volume of about 5 kiloparsecs. In the case of the least massive galaxy H074, there is no gas particles because they have been evaporated by this redshift because of the too low mass of this galaxy. Here I show evolution of stellar and gas masses in these galaxies depending on redshift. The solid lines correspond to the gas and dashed lines correspond to the stars. The number of stars gradually increases with the galaxy evolution due to star formation processes, while the amount of gas on average gradually decreases because one part of the gas transforms into stars, another is ejected due to outflows caused by stellar feedback and UV background heating during the reionization epoch. In the right figure, I show gas fraction in these 5 galaxies, and we can conclude that these galaxies are gas-rich, at least down to redshift 1. except for the least massive galaxy H074. In this slide, I show alpha or iron versus metallicity we obtained for the simulations. These data are for gas component in these galaxies, compared to the observations that we obtained in the previous work. First, you can see that alpha over iron gradually decreases with redshift, shown by the numbers as we expected from the theory. And the simulated data also show a trend in metallicity with mass. Because in more massive galaxies, the interstellar medium is enriched with metals faster. Overall, the simulated data overlap with the observations, and from this figure, we can conclude that the low determinate subsample correspond to the stellar masses between 10 to the 6 and 10 to the 9 solar masses, while the high determinate subsample is within 10 to the 9 and 10 to the 11 solar masses. We also found in the literature determination of masses of 3 DLA counterparts. And as you can see, their masses are higher than 10 to the 9. And these numbers are consistent with these numbers. Then alpha over iron versus specific star formation rate. Specific star formation rate is the star formation rate divided by cumulative stellar mass of the galaxy. From the theory, we know that high alpha over iron values trace intense recent star formation. In the left figure, I compare the simulated data with observations. The area shows simulated data. This is geo-simulations, and I also added the relations obtained from the TNG and Eagle simulations. You can see that all the simulated data are consistent with each other within 3 sigma confidence intervals, while they are not, the galaxies evolve from the top right corner to the bottom left corner. But the simulated data are not very consistent with observation. In case if the star formation rates are correct for this data, we may assume that the star formation was more intense in early times in these galaxies. So we think that star formation rates should be reconsidered in all these simulations. To obtain column densities and delta V90, we needed absorption spectra. To make absorption spectra, we used Trident, a tool specifically designed for this. And to build statistics, we created light rays crossing each galaxy at 12 view angles with the step of 30 degrees around X, Y, and Z axis, in such a way mimicking 36 view angles in total. And we repeated this procedure for different galactocentric distances or impact parameters. As a result, we obtained this distribution of column densities with galactocentric distance. You can see that I should say that these stripes correspond to the limits within which the galaxies appear as DLA, sub-DLA, or Lyman limit systems. You can see that the distribution of column densities in simulated galaxies evolve this galaxy mass. But even the most massive galaxy H000 does not reproduce the distribution of column densities that we know from the observations that which we found in the literature. While the Auriga and TNG simulations are better in reproducing the observed column densities, this can be explained that the Auriga and TNG and other more well-known simulations have been tailored to reproduce Milky Way-like galaxies with expanded disk. So if the measured DLA counterparts are mostly Milky Way-marked galaxies, it is not surprising that these models work better than GEAR in the high mass region. On the contrary, GEAR has been well calibrated to reproduce low mass galaxies, which makes up the majority of DLAs. And this disagreement of GEAR with other simulations and these observations can be attributed to insufficiently strong stellar feedback in GEAR. So the feedback should be reconfigured in GEAR. Then we also obtained velocity width using the same method as it was used for observation. And here I show some example of how we determined determinity. And then we can look at the determinity stellar mass relation. I also added the Arab-Salmanic relation because we used this relation in our previous work. But you can see that it's not consistent with both simulations and other observations. We also found in the literature, for example, from Müller, shown by the red and magenta low and high Z galaxies respectively. And from this data, you can see that high Z DLAs tend to be systematically shifted towards a higher determinity with respect to the low Z DLAs, which may indicate an evolution of the relation with redshift, which is also consistent with the simulated data. Plus, the simulations are consistent with the stellar relation, which everyone wants to obtain, is a stellar mass metallicity relation. In the left plot, I collected all the data I found from in the literature compared to the simulated data. Of course, metallicity is growing with redshift with galaxy evolution. But to simplify, selected only those data that correspond to redshift about 2. And I also added the relation obtained from the TNG simulations. And from this plot, you can see that all these data are consistent, except for maybe the relation obtained by Maiolino. And we can say that GR is particularly important for constraining the mass metallicity relation in the low mass range, which is not targeted by such projects as TNG or Auriga or Eagle, because the most well-known simulations are specified on Milky Way galaxies. And the last slide is for velocity width versus metallicity relation. This plot is a bit controversial. It's complicated to understand if the data are consistent or not, because at the low derivative end, the simulated galaxies reach quite high metallicities, which are not observed in real galaxies. And the reason for this could be that these low mass systems are simply missed in observations because the gas is not very extended. So the probability to have a quasar in a line of sight crossing the gas is low, especially at low Z. At the high determinative end, in the contrary, model metallicities are not high enough to produce the slope that we expect from the observations. And it is likely that a GR might not be ideally calibrated in the Milky Way mass regime. So to summarize, I want to say that simulations, hydrodynamical simulations, can be very effective in constraining DLA observations, but it's quite difficult to make simulations that would perfectly reproduce all the variety of observed galaxy properties. But still, such a comprehensive analysis helps to better understand the processes governing the formation and evolution of galaxies. Thank you for your attention.
Thank you for your talk. Please, questions?
I have a question.
Yes, please.
Yes.
Okay.
Do you hear me?
Yes.
Yes.
Okay. Maybe it's just my misunderstanding, but I don't understood what mean alpha elements. You not explain it. What is
Alpha elements,
Yeah.
yes. Alpha elements are oxygen, magnesium, silicon, sulfur, calcium, and titanium.
So this is relation between these elements and the ferrum and the hydrogen. Okay. Another question, what is DLA? Maybe you will explain more detail when you if you enter some abbreviature. You should to explain what is the mean, what is why it's important.
Then this it's shown in this figure. It's illustrated in this figure.
What does
DLA
mean?
is the system that consists of a galaxy and background quasar. So we see this galaxy in absorption.
So it is absorption of quasar continuum by galaxy.
Yes, yes. Exactly.
And it's only by galaxy or maybe intermediate sources in between, or it's just it is characteristic of a galaxy only. Yeah. It's not depends with a quasar or some other sources.
No, sure. The spectra, we analyzed spectra that were produced by the galaxies.
Okay. And the last question, what is the mean delta 90?
Delta V90 is the velocity width. So the width of
velocity of
the lines.
It's inner velocity of galaxy or some other velocity?
Yes, this characterizes velocity inside of the galaxy under study.
So it's just a sigma with okay, it's characteristic of the galaxy, of the mass of galaxy, yeah, or distribution of galaxy. What is it?
What do you mean by distribution of galaxy?
Okay, it's mean, for example, if the mass of galaxy distributes in isothermical or other laws, so it should be different. I know the sigma is a dispersion, velocity dispersion is a mass characteristic of most of the early type galaxies. So it's the speed of stars moving around the center. But what is the V90?
Yes, it's also dispersion. I would say that each galaxy can contain a number of clouds, and if the line of
Number of what? Sorry.
Clouds.
Clouds. Okay.
We study interstellar medium, so it can consist of some clouds, and each cloud has its own velocity, and the velocity dispersion of these clouds can characterize it's a dynamical property of the galaxy.
So it's a cloud inside the center of galaxy, you mean, or what? Which cloud you mean?
Cloud that the line of sight can meet. I mean, the ray can meet along the line of sight.
Okay. So now is more clear. Thank you. And another, I'm not specialist in the galaxy formation and other, but you mentioned that the different galaxies, it's when you simulate it, you write in H00, H0 for something,
Yes.
other numbers.
Yeah.
What is the difference between? It's a relation between what?
These numbers.
Yeah.
It's just numbers.
Just numbers.
How these galaxies have been called in their work.
Why these numbers? Why not 25, 75?
We just counted these galaxies, I think, and then they...
Okay, but I see, it's just a number for some random number of...
the galaxy from the simulation volume. Yeah.
Okay, you selected just a few of them and showed what is...
Yes.
And one more question. When at the slide next, maybe next. Yeah, here is. I see it's alpha ferrum, the metallicity relation. Is this characteristics depends with the evolution of galaxy? Because if I remember right, there is also should be depends with age of galaxy.
Yes, this I also said. You see these numbers. These numbers correspond to different redshifts.
Redshift, okay.
And you can see that alpha over iron decreases with redshift. Yes. With galaxy evolution.
And okay. Understood.
Everything is consistent with the theoretical expectation.
Yeah, okay, thank you.
Welcome.
Please, more questions?
Okay, if I can, thank you very much for the talk, interesting talk. I'm not an expert also in this field of research, so for curiosity, I have some questions. You said about this hydrodynamical code which you were used, And I want to understand, do you take into account, for example, the merging of galaxies? Because the redshift is really high, so this is around 4. And as we understand, it's exactly time around the main merging of galaxies. And in principle, it can be trigger to switch on star formation. So this is one of the questions, just to understand.
So the question is whether the star formation was triggered.
No, I ask another question. In this simulation, when you consider some galaxies, and you also speak about the evolution of galaxies, as we know, as we go in past, it was a time when it was much more merging effects of the galaxies. So in this simulation, for example, you consider this case to compare it with observational data. So probably you can say something about the stage of the merging of galaxies.
I didn't study this question, the merging. I was interested in the properties of gas particles, but I didn't go deep to the processes that was happening in the galaxy.
No, I just can see from the left that equal 4. And
Yes.
This, yes, it looks like this is merging of two galaxies. So it's asymmetrical like this. So probably because the idea to find something about cosmological process which was passed through a long time, and for example, the age of exactly in reionization when it was also the merging of galaxies like this, some cosmological parameters. So just I have a general question.
Sorry, I don't know how to comment this actually.
Okay.
I can give you a link to this paper where these galaxies are actually I didn't understand what you mean.
Okay, you consider the reason of the star formation, the trigger
No.
of star formation only outflow, only what's mechanism of star formation, and as a consequence, it also can be the additional metallicity and like this.
I didn't do these simulations. I only used the results.
Okay. No question. Thank you.
Please, another questions from audience? I have one also. When you mentioned stellar feedback and problem with strength of this feedback in gear simulation, what physical processes involved in this term? What means stellar feedback?
Stellar feedback. So when stellar process.
Yes.
So if there is some star formation, it can affect on the distribution of gas, for example. Yes. So if the stellar feedback is not strong enough, so the galaxy can be too concentrated or too small. I don't know.
I mean, I understand correctly. Sorry, can I add just the physics of feedback of the star formation like this? Not only star formation, but feedback from stars. This is also the explosion of supernova. This is shock waves, so like this, which throughout the gas around. just to understand really the physical processes of this, what about probably Ivan Grigorьevich asked.
Mm-hmm.
The physics of this process.
Yes.
Not physics, but exactly counting the processes that involved in feedback. Supernova explosions, probably stellar winds or winds from very massive stars, and so on. And
I think somewhere. So stellar feedback. So stellar feedback can cause outflows and UV background heating as well.
Okay, thank you. And another question was from about second slide, if you remember. Yes, here you mentioned that decline of the on this plot is due to supernova 1 type.
1A.
1A, yes. And another supernova type can give some impact on this process, like not white dwarfs thermonuclear explosion, but core collapse supernova.
Core collapse supernova mainly contribute to alpha elements. And that's why we see this behavior. At this stage, core collapse supernova contribute to the abundance pattern. Here, supernova 1A starts to add to the abundance pattern. And that's why, and they produce more iron. And that's why we see this decrease.
Not change of alpha elements, but
everything is changed. I mean, everything is changed. Alpha elements or the metallicity, overall metallicity grows.
Yes, yes. Metallicity grows, but alpha elements.
This is about ratio of alpha elements and iron. They are both increasing, but the ratio between them is changing, you know?
Yes, thank you for explanation. Now I understand. Please, another questions? If we have no questions, thank you very much one more time for your interesting talk. And see you on the next seminar.